All right. We have, okay. All right. So now with the general idea, let's actually start to discuss how do I solve differential equations with that idea. Finite element actually, again, doesn't solve any differential equations equally easily. It helps you solve the kind of differential equations that naturally lends itself to a minimization of something. And the minimization of something often turns out to be energy. That's actually one of the reasons why finite elements are used so much in structural engineering, right? Because in structural engineering, a lot of the equations we are solving naturally by itself is actually an energy minimization problem. Okay, let's actually discuss why that is the case through a very simple example. Okay, so I'm actually describing a structural engineering example, and the example is the following. I have a string. I have an elastic string. Okay, anchored over here. So the string is anchored over here. The other side of the string is anchored over here on another wall. When the string is not loaded, that means nothing hangs on the string. Okay. Also, suppose the string doesn't have any weight by itself. The string doesn't have any stress on it, and it's just a straight line. Okay. That's when nothing hangs on it. Now, suppose I start to put a distributed load on the string. So I don't just hang one thing or a finite number of things on the string, but rather I'm just going to pour some sand, let's say, over the string. So I have a distributed load. The load is a function of x. So f of x is the weight density, is the weight per unit length. All right. Under the load, the string would actually lengthen, right? It would go down. So the string would look like something like that because it's loaded. It goes down. All right. So the question is, what is the shape of the string? So let's say the shape of the string is u of x. The question what is u of x? All right. How do we proceed in figuring out this problem? Physicists usually have two different ways to analyze such a problem. One way is a macroscopic analysis, and one way is a microscopic analysis. And what's interesting is that they arrive to the same kind of equations. And the microscopic analysis directly leads to a differential equation, while a macroscopic analysis leads itself to an energy minimization problem. And the energy minimization problem can also be converted naturally into a differential equation. So let's actually pursue the energy minimization strategy first and see how this goes. So before we talk about energy minimization problem, can somebody tell me what are the kind of energies that appear in this problem? What type of energy do we have?
Potential.
A potential energy, that's great because I'm putting weight, right, on the string. So we have potential energy. The potential energy would decrease if the weight goes down, right? If the string deforms more so that the weight actually can be lowered, the potential energy would decrease. Okay. If the string deforms less so that the weight doesn't go down as much, the potential energy is going to be more. Okay, what other energy do we have? Oh, what I was talking about is just the gravitational potential energy, right? There is another type of potential energy in this problem. What is it?
Elastic.
What?
Elastic.
Yeah, elastic potential energy, right? So I have actually two types of potential energy, the gravitational and the elastic potential energy. And elastic potential energy actually goes the opposite way, because if the string deforms more, yes, the weight actually can go down more, and thus I have less gravitational potential energy, but I have more elastic potential energy because the string have to deform more, right? It has to lengthen more. So there is a kind of a balance. So I can, if you can draw this, let's say this is a very non-rigorous hand wavy way of describing this, but like if this is the deformation in some sense, right? And this is energy. Okay, I have two energies. I have some kind of a gravitational potential energy that looks like this, right? When I don't have any deformation, this is a 0, and if I have deformation, the gravitation potential energy would decrease. Okay, I have another type of energy that's elastic potential energy. That's more like that, right? In the beginning, usually the Hooke's law goes like squared, right? So I'm drawing like something like a squared. So this is the elastic potential energy. Okay, and when you sum them up, you get a curve that's more or less like looks like that. So this is the total energy. Okay, and when the system reaches equilibrium, it is going to be at a state where no matter what you do to the system, how you deform it, it will not decrease the total potential energy further, which means it is at a point like that. Okay, so but the problem is, of course, the deformation of this this string is not a one-dimensional. It cannot be described by a single parameter because it's a continuous string. So the deformation is not a one-dimensional parameter you can increase or decrease just by sliding a slide bar. It's actually an infinite dimensional function. So here we have to figure out a way to minimize the total energy by sliding an infinite dimensional slide bar, right? Which is this U of X. And let's figure out how that works.